All right, so the next talk is Biparsers exact printing for data synchronization. Ruifeng is presenting, and stage is yours.
Okay, thank you. Okay. So hi everyone. This is joint work with my supervisors Tom Schrijvers and Zhenjiang Hu. So as the title says, we are going to tackle the problem of data synchronization by using a technique called exact printing. And the final result of our system or theory or framework is called Biparsers. So let's start with the problem itself, data synchronization. Here's a very simple example of the same data being stored in two different copies into different data storage formats. And as you can see, they are currently synchronized. So the synchronization between the two formats can be done by introducing a new shared data structure for both of the formats. And the transformation between the two can be think of as the composition of a parser and a printer. So we can see you can go from the left to the right by applying the parser of the right and applying the printer of the right. And the other way around is also works. So in the big picture, we have some textual representations, and we have a shared data structure. And we want a pair of parser and printers between each representation and the data structure. So this is what's expected from the whole synchronization scheme. If we start with a pair of synchronized data files, and we perform some edit on one of them, we expect to be able to synchronize the edit first back to the data structure, and then through the printer back to another data file. So as we can see here, we actually want to achieve some local edit, and we want the formatting of the original file to be preserved as much as possible. But this can actually go wrong and will go wrong if you are using some existing parser and printer frameworks to do this. So we summarize the problems as two challenges. The first challenge is the non-injectivity nature of the parser as a function. And this is in conflict with the requirement of exact printing. So we do the edit, and we try to print it back. And we see the edit is reflected back, but also the formatting is messed up. We see that the comments and the white spaces are lost. And the representation of the string data is in a different format. And also the written forms of the integers and the Boolean values are also in different format. So this is obviously not good. So the summary for this is that we need to remember the lost information of the parsing process somewhere. And we need to try hard to recover the formatting in the printing process. The second challenge is that there are some consistency issues between the parser and printers. So this time we apply a slightly different edits on the JSON file by introducing this suspicious colon space into the string. And if our printer tries very hard to preserve the original formatting, we get this file. And this is illegal. This is invalid syntax in YAML. And even if it is valid, this YAML file means something different, because a string is turned into an object. So the summary for this is that we want to try very hard, but not to try too hard to recover the formatting. And we need to be careful when the text would change meaning. So our solution to this problem is our biparsers. Actually, if we put the parsing and printing aspects aside, we already know how to synchronize data. And the solution is called bidirectional transformation, or lenses. The idea is that we start with a pair of data, source and view, the two data to be synchronized. And we start with this original source. We perform a get operation to get the extracted view. And this get function is not injective. So that's where the non-injectivity problem happens. and we perform some edits on the view, we cannot directly put back the view alone because of non-injectivity. What we should do instead is that the get function should also extract something called a complement. And this complement saves the lost information in the get operation. Now we can combine the complement and the modified view so that we get back the updated source. This is very good, but pure lenses, they are pure, so that they cannot handle the parsing and printing effects. For composable parsing and printing, we already know that we need some P monad, the parser or printer monad, which is basically state monad plus error monad. So biparsers are essentially lenses, but generalized with monadic parsing and printing. So we combine the orange part and the green part into this definition. So we introduce the P monad into both directions of the lens and get the parse and print functions. And after this, existing definitions and properties for lenses also need to be generalized to take into account the new P monad. So the first thing to generalize is the basic correctness properties for lenses, which is called round-trip properties. It's a very happy thing to notice that generalizing the round-trip properties actually coincide with addressing the two challenges we have mentioned. So the first challenge was that the requirement of exact printing requires that every data that is parsed can also always be printed back to exactly the same form. So as an example, we have some different textual representations. They are parsed into the same thing. So apparently, if we directly print it back, then we get one of them, but not all of them. So this is not acceptable. Actually, we want them to be reflected back to the original formatting. This requires we save some complement, which is the lost information, to be able to recover the formatting. And the second challenge was consistency, so that every printed text can always be parsed back to the same data, so that the meaning is not actually changed. This is the example we see. So we have this colon space thing. If we print it with the unquoted format, then everything is messed up. But this means we have to print it in the quoted format, and it should parse into the same thing, and everything is good. The second thing to be generalized is the composition of lenses. So because we introduced the P monad into biparsers, we change from pure function composition into Kleisli composition of Kleisli arrows. So we see that the complement is accumulated. And the composition here actually combines two aspects. First is sequencing for the parser and printer effect, which is the P then Q structure. And it also has the piping structure for transformation. So the first transformation is from X to Y, and the second is Y to Z. So the combined thing is from X to Z. And our main result here is that this composition operation, this generalized composition, preserves the round-trip properties, which enables compositional programming so that we can actually combine small biparsers into larger biparsers. And during this process, all the round-trip properties are automatically derived. So we automatically get the correctness guarantees for them. And based on this definition, we provide a rich combinator language to write biparsers, which we call biparser combinators, which is based on the classical parser combinator frameworks, like Parsec in Haskell. So usually, these frameworks consist of 4 different parts: token consumption, sequencing, and alternation or choice, and filtering, which is validation and transformation. So by analogy, we define biparser combinators. The main challenges here are that, first, to take the complements into consideration, and second, to make sure that all these combinators preserve the round-trip properties. As I have already mentioned, that composition is sequencing and transform combined, so we have already 2 of them addressed. And actually, the hard part is for the choices. I will not go into all the technical details. I will just show you an example. This is a grammar for JSON strings. It's a simplified one. So as you can see, we have all these EBNF generation production rules. And we can just directly follow the structure of this grammar to define the parsers using parser combinators. And the parser resembles the grammar structure. So we have the combinators for sequencing, combinators for alternation, and combinators for transformation. So the same thing would happen for biparsers. As you can see, this page is very similar to the previous one. So that means the biparsers also resembles grammar, but it also resembles the parsers, which means if we want to develop the biparsers from scratch, we can do it easily by following the grammar structure. But if we already have some parsers, we can also migrate it fairly easily. So here are some highlights of our solution. First is that we made it compatible between lenses and effects. So as some of you might know, in previous works, there are some serious restrictions on how effects can be used in bidirectional programs. We solved the problem for parser and printer effects specifically in two key points. So first is we use complement-based lenses instead of the SV to V-based lenses. This avoids getting into lens compositions, which makes the composition preserve the round-trip properties. And it also has some other benefits, which you can check the paper to see. And the other thing is that we require effect cancellation instead of effect preservation, as in previous works. So this means print would rewind the effects performed by parse and vice versa. And this fits our purpose perfectly and simplifies the theory. The second thing is what I mentioned just now, the choices. So for a parser framework, we need backtracking choices. But in a bidirectional parsing context, there are some consistency hazard happening in the choice combinators. Because parser combinators rely on shallow backtracking for choices, which means if you have a P or Q structure, first P is attempted, but only if P fails, we fall back on Q. This means if we have this situation, we start from some X, we parse and we parse with P and fails. Then we fall back to Q, which succeeds. And then we attempt to print it back. But since P is still attempted first, and it might succeed in this case, in which case the Q branch is never attempted. So this results in some inconsistencies between which branch is actually chosen in the execution. But parse Q and print P are completely unrelated, so they have no guarantees whatsoever, which means this round trip, we have no guarantee for it. The solution here is that we have some different choice combinators for different preconditions, which would ensure that no such branch mismatch would happen. And there are some more features, you can check them out in our paper, and I will not get into the details. Finally, we have a complete proof and a runnable example. So we implemented the whole framework in Agda and Haskell. We have mechanics proof in Agda, all the combinators with the round-trip properties verified. And we also have a runnable example for subsets of JSON and YAML. And both of them are available as reusable packages, so you can check them out. Finally, to conclude, we present biparsers with exact printing and for data synchronization. This is lens generalized with monadic parsing and printing. We have formalized consistency for it, which is the round-trip properties. And we also support compositional programming with this main result. And we provide a rich collection of combinators to construct practical biparser examples. And yeah, thank you. And more details in the paper.
Any question for the speaker?
Just a small one. I think I saw it flash by on one of your slides, but you can use this as just a pretty printer, right? For like, if you have a data structure, you could throw it through the pretty printer, and you don't need to have some weird special context in terms of an original parse in order to use this.
Right, right, you can. The problem is, as you see here, the formatting is lost. So I think in a lot of actual situations, for example, you have two people collaborating on the same data source and they have different preferred data formats, then it wouldn't be very polite to see that your formatting is lost after my change. So I think that's one of the fundamental flaws of existing pretty printers.
Thank you.
Hi, I'm Pafonia from Minnesota. And I have a question about the preserving the format. For example, if I change the word status to some word that is very long, will the properties and the YAML file still be aligned?
Right, right. That's something you need to take care of when you write the biparsers. So there are actually something we sorry. No, sorry. Anyway, we have this view complement alignment operator, which allows you to adjust the internal structure of the complement. So as I said, all the white spaces and comments, they are saved in the complement to be recovered. And you get an opportunity before printing to actually manipulate the complement to fit your purpose. And yeah, so that is possible, but you need to do it manually.
Hello. Nice work. I have a question of when you apply a choice combinator and the first phase fails or success. I mean, the second case success, and you print it back. You said it might be that the first branch succeed. Why would that would happen? Like right here.
Yeah. So this is only one of the example. You can also have print first, and the second branch of print succeeds, and the first branch of parse succeed.
Yeah.
So you also have a mismatch there. To prevent both of them from happening, we have some special preconditions for applying the choice combinator.
Yeah, the question I'm asking is what would make those like, what kind of inconsistency is there?
Okay. So because if you have the parser from P and printer from Q, you essentially have no guarantee about their relationships, right? So if they are from the same biparser, then you have the round-trip properties. You are guaranteed that they are consistent and you get the exact printing behavior. But if they are from different biparsers, then you know nothing about them, which means anything can happen.
So yeah. It means in general choice, the alternate combinator is just not round-trip, so correct, or something like that?
Yeah, so if you do not pose any requirements on the two branches, then anything can happen. You have no guarantee.
Thanks.
All right, then this concludes the session, and let's thank the speaker again.